Hi everyone, welcome back. In today's video, we're going to dive into the essential concepts that you need to master when working with Web3, especially on Solana. These concepts are fundamental to understanding and how to interact with the blockchain securely and efficiently. So let's break them down one by one. And in today's agenda, we're gonna talk a little bit about Keypairs, public and private keys, and understand what they are. Wallets, understand what wallets are. Solana tokens and accounts. Everything in Solana is an account. We're going to talk about transactions and what it means to have a atomic transaction or atomicity. It's a difficult word to say. Program derived addresses, or PDAs in short. PDAs are a concept that you're going to be living with in your journey of working with Solana. So it's a really important concept that you need to really understand what it means. And then I'll give you a glimpse of what's coming in the next video. So let's get started. So, and these important, just before I begin, so these concepts are really important that you grasp what the meaning of the words is, and you need to understand these before I show you any code, because otherwise the code will probably not make much sense to you. So in order for your development experience to be meaningful, it's important that we go through these concepts so that in the next session, I can, when I show you the code, you'll start connecting the dots and say, okay, this is what it means. So let's get started. So key pairs, public and private keys. So in blockchain, one of the most fundamental concepts is the key pair. There is a public key and a private key. So the public key, think of this as an address in the blockchain. It's not sensitive and it can be shared with anyone. This is where people send tokens or data to your account. When you share your wallet address with someone so that they can send you some USDC or some Solana, you give them an address, which is the long string that everyone knows is associated with their wallet. That's your public key. That's the address. That's what they paste into their wallet when sending you tokens into your wallet. Private key. So this is the proof of ownership, effectively, all over the account that corresponds to that public key. So they're linked, the public and private keys. So the private key, as the name implies, must always remain confidential because it's what gives you access to your assets. If someone gains access to your private key, they control effectively your account, and they can take your tokens. So this is why protecting private keys is of the utmost importance, especially when running decentralized applications in environments that you don't fully control, such as a mobile app or web apps. And you know, there are special precautions that you need to take depending on the type of wallet, but we'll get into that shortly. So in cryptography, there is asymmetric cryptography and symmetric cryptography. We're not going to talk much about symmetric cryptography because it's basically encryption, decryption with just the one key instead of two keys. But what we care about for this topic is asymmetric cryptography. And yeah, it uses a pair of keys, public and private keys, as we just discussed in the previous slide. And examples of this are RSA and ECC. And these are very well-known public-private key algorithms. So in terms of encryption, any data encrypted with your public key can only be decrypted with the corresponding private key. That makes sense, right? So this is an incredibly powerful concept, especially in use cases like e-commerce, where sensitive information needs to be protected. So if I want to send you a message, you give me a public key, I encrypt it with your public key, and no one but you, because you own your private key, can decrypt it. So, and if you think about it in the context of an e-commerce platform, there are really interesting use cases for this. And I will show you one that I used exactly to take advantage of this, so that sensitive data that I wanted to record on the blockchain, everyone knows obviously the data in the blockchain is public, everyone can see it. So I had to use encryption to actually record that sensitive data in a way that no one else can see it. But we'll get into those concepts in an upcoming video. And then you have signatures. Data signed by the private key can be verified by the public key. So this basically allows the blockchain to confirm that the data came from the owner of the private key without revealing the key itself. And that's the key point, right? So if using the private key in this way allows whoever receives the message to categorically prove that I am the sender of that message, because only I possess that key, if obviously again it was not leaked. In terms of wallets, and by the way, I know these concepts are sometimes difficult to wrap your head around, and even I've worked with this for many years, and sometimes I still need to refresh my memory on how all of these things work, because on and off, for instance, I need to generate a digital signature of a document programmatically, that is, and I need to refresh my memory. Okay, how did this work exactly? Okay, I need to produce a hash of this, and then use this algo, and then use this key to sign the hash of the message and whatnot. So all of these elements are. I'm not intending for you to finish this session with becoming an encryption decryption expert. That's not the point. The point here is for you to at least have a high level grasp of the concept, so that you can, when you look at the code, you understand what the code is doing. Because otherwise, as I said, the code would be a little bit meaningless if you were just replicating it without really understanding what it's doing. So wallets. A wallet is more than just an interface for a blockchain. It's a container for private keys, and it handles the critical tasks like signing transactions. So remember, as I just described with your private key. So simply put, wallet contains your private keys, and it's responsible for authorizing the transactions. There are a few types of different wallets. There are hardware wallets, of course, and there are software wallets. The hardware wallets, like Ledger, for example, store keys offline in a hardware device, providing a lot more security. And then there is the concept of a software wallet, like Phantom, for example. And these are obviously very convenient, but they are more vulnerable because they're not isolated from your computer, which may be attacked by malware and viruses and things like that. So, you know, wallets like Phantom kind of run as plugins in a browser. If you're in a mobile app environment, you will see that in the upcoming videos. You could have the app installed as an individual app that you can download from the App Store, and you can use deep links to communicate with the app. But effectively, yeah, these are kind of the two big categories of wallets: hardware wallets and software wallets, or sometimes known as cold wallets, as in hardware wallets, and hot wallets, as in software wallets. Sorry, these are all the terms. You probably, most of you, if not all of you, listening to this already know all of these concepts. And then signing transactions, whenever you perform, obviously, any blockchain transaction that requires you to sign something, you know, like transferring SOL to someone, your wallet signs the transaction using your private key. And you will be familiar, of course, when you're using your wallet to sign something, a pop-up comes up in your browser, for example, asking you, you know, should I go ahead and assign, you know, and go through with this transaction? Please approve this. You click approve or yes, and then effectively what happens is, behind the scenes, your private key is being used to sign the transaction, which is then sent to the blockchain. And then the blockchain obviously validates that your you know, that the transaction has been signed by the sender of the request. One other aspect that you can see on the screen is that, and I took this picture straight from the Solana documentation, you can see that there are various addresses here, and this is the elliptic curve encryption. And as you, effectively, what this means is, when you generate a key, that address must fall on this curve. And this is what you see here. So you see a number of, at least a couple of wallets here represented. And that means that when the address was generated, yeah, or a key pair was generated, the wallet address falls on this line. Now, with PDAs, as we'll see later, it's different, but at least for, you know, public-private keys that kind of fall on this line. One of the things that it's important, and this is obviously a mathematical function. Again, we don't need to go into the details of this, but again, the point here is when you're generating keys, the generation of the key doesn't do anything on the blockchain, right? So this is one of the concepts that I initially, when I started, I was like wondering what happens with, like, when I generate a key and I call this method or this function from this library to generate a key for Solana, does that actually do anything? Probably not, right? But I wasn't quite sure about that. You know, does that space get allocated in the blockchain somehow? The answer is no, it doesn't. So just having a key generated doesn't do anything. It doesn't, you know, the wallet effectively doesn't, you know, materialize out of nowhere and comes into existence in the blockchain. The only way that happens is if you actually then send a transaction to the blockchain ordering a transfer of a certain amount to that address. And then at that point, yes, the wallet comes into existence and the address is initiated with a certain balance that you sent to that address. That's how it works. That's one of the things that initially I was kind of trying to wrap my head around, how this actually works in practice. And, you know, there you go. That's the answer. So generating the key doesn't do anything on the blockchain. What you know, that address becomes actually physically a wallet the moment you actually send something to that wallet address. Solana tokens and accounts. So on Solana, everything is represented as an account, as I said before, and the native token is Sol, which powers the network by paying for transactions and rent on accounts. That's kind of one of the uses of the Sol token. A fun fact is that one Sol equals 1 billion Lamports. Lamport is just like Satoshis on Bitcoin. It's the lowest unit in the token. Accounts on Solana are used for everything, storing tokens, NFTs, program data, etc. Then you have the other thing that is important to understand is, we talked about this already, is addresses. So these addresses are often shown as base 58 strings, long strings, as you can remember, and they are, the mechanism that we interact with accounts on the blockchain. So we basically, whenever we want to do anything with any account, we have to specify the address, the base 58 format address. So now a little bit about transactions and atomicity. That's a difficult word to say, as I keep saying. So Solana transactions are at the core of how you interact with the blockchain. So a transaction is simply a collection of instructions that invoke smart contracts or move tokens on the blockchain. So another analogy that I often like to use, and this is really useful for someone that comes from the Web2 space, is, you know how APIs have their HTTP endpoints like post, get, delete, all of these HTTP verbs like for each of these endpoints. Think of those. It's the sort of the equivalent here is instructions. So your Solana program is like an API, and within it you have instructions, which are effectively the endpoints of the API for post, get, etc. So think of it, it's not quite the same, but it's similar. So if you think about it like that, and a transaction is comprised of one or more instructions, where you send these collection and they're executed in a certain order if they affect the same account. If not, they can be executed in parallel. The Solana runtime is actually quite clever, and this is one of the reasons why Solana is so incredibly fast, is that it knows which instructions are touching on which accounts, and if they're not the same, they can be executed in parallel, which is, amazing. So what are effectively atomic transactions then? So Solana transactions are atomic, meaning that all instructions in a transaction must succeed or the entire transaction fails. This is crucial for ensuring data consistency, and it's similar how basically databases work. So if you've come across the concept of atomicity in databases, in Solana is exactly the same. So it helps to think about it in those terms. It's the same as databases, atomic transactions. And finally, just to give you a real world sort of example, in our e-commerce decentralized application, a single transaction could transfer SOL from the customer to the business. So to my business, if you purchased a product from me and you pay with your SOL, the transaction will include that transfer instruction from the system program. So this is one of the things that you'll learn, is that you'll use different programs. Some of them are your own program. You created a custom program. It's effectively your smart contract that you you're calling an instruction from your program, but you could also be calling an instruction from the system program. So you know, in this example that I'm giving you, it means that the transaction has two instructions, one of which says, please transfer me this amount of SOL from the customer wallet to my business wallet. And then you have another instruction that actually does call your Solana program, and the whole goal of that instruction is to create a PDA account, as we discussed earlier, where it stores that metadata associated with the purchase order, so that you know, because the transaction is atomic, if the purchase order was created, you know 100% certainty that the Solana transfer also happened, and therefore the two things go together and are recorded in the blockchain. Talking a little bit about program derived addresses, as I was just giving in the example, I should have actually put this slide before the other one, but anyway. So in Solana, PDAs are unique account addresses that are derived using a set of deterministic rules. PDAs effectively are addresses that programs use to store data. So a program is an account, but it's marked as an executable account, so it has a code that runs. And then PDAs are data accounts effectively, and these are the places where the programs actually write data in. So what makes them special is that they don't have a private key. So these are addresses that do not have a private key, and are instead generated deterministically using seeds and the program ID, for example. So you see an example of this in this picture. So what you're saying here is there is this method that you'll see in the code that I'm going to share with you in the next few sessions, where you call this find program address, you pass some seeds into it, and the program ID, and then with, you know, one of the seeds could be, for example, your customer public key that I can obtain by just connecting to your Phantom wallet, and then I run that. You know, with those seeds can be any number of data points, but you know, one of them in this example is the wallet public key. And combining that with the program ID, that means that I can generate a unique address that is the PDA address that we are talking about, and then that address can be used by the program to write data into it. In our example, the PDAs will store, you know, as I was saying, order data for our e-commerce platform, and these addresses help avoid sort of having to keep track of all the addresses. Why? Because the only thing you need is the seeds. So if you know how to generate the address, that's the only thing you need. You don't need to keep a track of all the addresses that have been generated, which is super useful, because otherwise this would become a massive headache. So looking ahead, so again, I know that these were difficult, like very, very super high level concepts to grasp in just one session. If you want, obviously, the full details, the Solana documentation is excellent, and I took all of these pictures from there. But yeah, so this wraps up the core concepts that you need to understand when working with Web3 and Solana. From, you know, we talked about Keypairs to, you know, PDAs and wallets and accounts, We talked about all of these things. So these are concepts that are essential for developing secure and effective decentralized applications. And so in the next video, we'll dig deeper into how to implement these concepts in code. Please don't forget to like, subscribe, and hit the notification bell to stay updated. Stay empowered, stay decentralized. Thank you.